I have no doubts that you, no doubts, I have confirmation that you excel really great in doing research and accumulating data, but there were requests to resolve ambiguity, how to put it in writing. And the writing is due in 2 days in class if you are printing, if you're coming and printing. If you are preferring to do online, then you don't need to do it at night before. Like midnight, send me the file. So the reason why I'm requesting this, in the class, we will pretend that each of us is a reviewer of works of someone else, right? So I will collect and distribute. If everyone is in class, it's easier, just toss it and everyone gets it. If it is, if part of class online, then I will probably ask everyone to bring, we will be in the lab and computers are there. So you do not need to bring your personal computers, you will log in and I send you the link to Google Docs, you download the paper that you need to edit, and then I'll also distribute the reviewer, the templates for reviewers report. If you worry about your identity, I will make an effort to hide it, so you, the reviewer doesn't know whom he or she is reviewing. If you all are voting, we can do it open way. It may save a little bit time, but I'm ready to make hiding procedure. So I will like scratch through the name and put like numbers 1, 2, 3, or put symbols like diamond, star, sun, cloud to identify. So advise me by email, or we will make a little vote when it will be time. Okay, so what I'm going to tell today, there will be I think three sections of what I'm going to mumble in the next hour. So first, I will briefly review what you have done, with no attempt to make a complete review, or just some brief impressions, because some of you were already sending me data in the form of like PowerPoint or Microsoft Word, and I'll briefly skim through how I see your data, how to interpret it, how to group them. Second, I'll tell general vision of how to organize your writing, what to put in the text. And third, I will go over this little template of the reviewer's form. So what you will feel by reading the paper of your classmate. And I do see there is a something in the chat line. Check it. When it begin open things we all know who's doing. Oh, I am fine. Okay, yeah, thank you, Crystal. Yes, I think hiding identity in this situation is not as smart. But I'll ask double check. Maybe someone is sensitive to this. Okay. This is answer working. Yeah. Okay, so there are three materials: ferromagnetic, paramagnetic, antiferromagnetic. And for each of them, one can either characterize dosing time per state, or heat capacity, or the magnetic field. So you're encouraged to talk both vertical and horizontal connections. And for reviewers, I plan that each will make reviews of 2 works. One of someone in the same method, and one from someone in the same material, so that everyone will get feedback both on methodology and material aspect. So if we want to pretend or to play, to mimic the real world, we can organize it as several journals with several editorial committees, and those who are focusing on the density of states can be considered as submitting their work to the Journal of Microstates, right? So Kim, Crystal, and John, right? And here is the reviewing form. I'll probably resend it, and you will fill it and forward back to the author, so the author knows what you think about the work, in order to improve. And what else? The materials which are due before next meeting are the first draft. After you get feedback from reviewers, there will be final draft where you implement the criticism of reviewers. So we pretend everything as it happens in real life for scientists. You do something, you get reviewer reports, and then there are very rare situations when reviewer tells it is so bad you cannot publish, and it is very rare when reviewer tells it is so nice that it can be accepted without changes. It's like maybe 5% very bad, 5% very good, and 90% is when just follow these instructions, make a little improvements, and feel published. Okay, so ferromagnetic spin. So here is a figure that Crystal did share with me, and it is a study of microstates. So what is shown here is the density of states at different values of magnetic field. And one can identify that as magnetic field increases, the microstates take wider and wider space, or wider and wider energy. So if the magnetic field is truly close to zero, then all states have degenerated to form just one big peak. If it is a little bigger, this peak gets broader, and if it is noticeably large, then it spans over larger energy. So this understanding is quite important for interpretation of other results, and those who are, speaking of it, preparing the foundation and soil for interpretation of results that others are preparing. In addition to figures like that, you can compute the degeneracy for each of the peaks just by permutations, and compare what you compute with results of this density of states, right? And also, I'm going to show a figure from a project in completely different class, where it shows how to interpret each peak in a similar circumstance. So please do not take the next figure I'm going to show on the next slide as a literal instruction for activity, but each just as a little inspiration what can be done. So I'm preparing you for the next figure. First, you all know how to plot a microstate by these little sticks up or down, right? And each peak corresponds to a certain number of unpaired states. For those who would be listening to your talks for the first time, if you will have guests or from not from the class, from a side, it still needs to be explained what it is. And there was another Crystal. How can one? Is it possible to show images of multiple microstates and combine them with such style of density of states? So here is an example of something different from molecular modeling, molecular orbitals in computational chemistry class. It also extensively uses the concept of density of states. And then one can plot orbitals. You see there are little clouds. I think they're orange. And they are arranged near this molecular model. So one can just plot several microstates and connect them by lines with individual peaks. Of course, nothing is mundane, but if you try a visual style like that, it may help unbiased audience to understand what you're doing. Does it make sense? Crystal? John?
So a question about connecting the picture of the microstate to the density of states.
Mhm.
Um,
What's the reason, or you have a technical question?
Technical question, I guess. Looking at the microstate, would we see how many, like, what the total spin of it is, and then correspond that to the peak with of the same spin?
Correct. Yes.
Okay.
Of course, you cannot show all 60,000.
Mhm.
You show only one. And the reason, if we all in class know what we are doing, is there a reason to show this trivial information? Yes, I'm going to prove that. Because depending on your J parameter, positive or negative, the nature of the lowest and highest peak will flip. And it will be, it's a little bit trivial for us, but for side audience, it will be kind of discovered. So the distribution will look almost the same, but the nature of the lowest state will be completely different.
Okay.
Okay. So although it seems even up to this minute, Crystal, John, and Sahib may think that you are doing the same thing. You are not. Your result of this style will be different, and one would be able to learn something from this studies. Okay.
Thank you.
Next, Journal of Heat Capacity. So it is Chamberlain, Ichi, and Hyde, right?
Yes.
So here are one of the figures that I got from Ichi. So she looked for a specific heat as function of temperature, and it looks like there is no response. System doesn't accept energy, and then it accepts energy like crazy, and then it comes to lower rate of accepting energy as we heat it, right? So, and it happens, it is temperature to J ratio. J is typically quite small value. So this, do not look on this 100, 200 as absolute temperature in Kelvin. Absolute temperature will be lower. And we do not polish units because it would take a little bit more time. Just for this short class, it would take another week or two to debug and make units correct. But if we decide later after the class to collect all your contributions and make one single paper, then we'll polish it. So there is a peak, and later on one can check if the sharpness of this peak depends on the value of magnetic field. But there are experimental results exactly on the material that we are studying. And these experimental results show the specific heat as function of temperature, which on the global scale, it goes up according to Debye model that you covered in the previous part of the class. And it goes continuously and then a little slower. But this Debye heat capacity of a crystal has unusual peak below 10 Kelvin for this realistic material. So suddenly heat capacity rapidly increases and then rapidly drops. So it's experimental observation. And if I didn't send you references, I will send it to everyone. You have it, right? So you can briefly just give reference and overview what it is. And then it looks like this computation by each and this experimental result match each other. So as we increase temperature, something is happening at a specific value of temperature. System readily accept energy at high rate, and one can try to interpret what is happening. So typically, it is a well, I'll leave this explanation to you guys, but typically it happens during the phase transformation when like all-oriented antiferromagnetic come to all-oriented ferromagnetic. And in the border, there will be quite large number of states that are accessible by heat. So try to analyze. The bias and Chamberlain we'll have similar things for a little less challenging but still important things for paramagnetic and antiparamagnetic. And the dependence can be drastically different. It may appear at higher temperature. It may have much broader width, and the interpretation can also be different. Just what we discussed just before we started the slides, it would be really great to have several figures like that on one panel. Okay, Journal of Magnetic Susceptibility. So the CHEM759, Payment Avicii, Tyler Clark. I was in Russia, so I didn't have time to type the last name, but I remember your names. So here is the result from payment. I'm going to move the so here I'm not hunting for completeness of presentation. It's just little snapshot of your results, just giving you a flavor. So here payment computes average energy as function of magnetic field. And one does see that at low magnetic field, energy is not responding. It still stays basically zero. Then it starts changing rapidly, and then later it becomes linear, proportional to magnetic field, right? This negative slope. So in order to interpret this data, one can use the foundation, the help from Christoph. So once again, Christoph did show that as magnetic field increases, overall density of state becomes broader and broader. So if the magnetic field is close to zero, all microstates are degenerate. And no matter whether your spins are along magnetic field or against magnetic field, all energies are zero. So no matter what magnetic field is, the average energy will be zero, right? And then as the magnetic field increases, it becomes broader, right? And the states that are oriented along magnetic field will become more energetically favorable. So their energy becomes negative, and as they are getting populated, the average energy becomes negative. And as magnetic field continues to increase drastically, we will get isolated ground state, and all the ground state will contribute to the energy, to the average energy. So as magnetic field increases, this ground state will go to negative value proportional to magnetic field, and it will linearly contribute to average energy. So based on foundation results of those who focus on density of state, one can interpret observations made in the about energy and magnetization with scanning magnetic field. Any quick questions about this? Does it make sense? Okay. So another snapshot. CHEM7. So he is looking ferromagnetic, and here are some of his results. The x-axis is magnetic field, and y-axis is magnetization. So it's different style of result than in previous figure because I'm making a snapshot. So if temperature is large, this panel, and it's like 1,200. At zero magnetic field, magnetization is zero, right? Because temperature promotes states from slightly lower energy to slightly higher energy, and microstates with non-zero spin and zero total spin are approximately equal in energy, right? So there is no the average magnetization by adding together those that are parallel to magnetic field and anti-parallel and zero spin will result to zero total magnetization. As we increase magnetic field, the energy degenerates, and these states with, that are along magnetic field becomes more energetically favorable, and they are more highly likely occupied. So after averaging only over this occupied state, the magnetization becomes more and more negative. And after some value, there will be only ground state with full magnetization minus 60 in our model, right? And then it doesn't change on temperature anymore. Make sense? Then, if the temperature is zero or as close to zero, then no matter if magnetic field a little higher than zero, then still the only ground state will play the role. So if just little magnetic field is available, then even at and temperature is zero, then always with some numerical errors, ground state will be occupied and will give full magnetization. And as we go from lower temperature to higher temperature, there will be transitions with some numerical noise and then some sharp change. But at higher temperatures, there is continuous change from zero to maximum magnetization. At lower temperature, it starts immediately from maximum magnetization, which is called spontaneous magnetization. At 0 Kelvin, ferromagnetics are already in magnets. And so this zero low temperature for like iron is quite high. So you take a piece of iron and feel the magnetic nature. If you heat it up, it will stop being magnetic. If you cool it down, it will become magnetic. So this is related to the concept of spontaneous magnetization. So before, like, if the phase diagram in excess of magnetic field and temperature, if magnetic field is low, it will be ordered, which means all spins the same direction. If it is higher, it will be disordered and will correspond to this average zero magnetization. So it's quite interesting interpretation of the work that Xinjiang is doing. Okay, any questions? And here is the work of Tyler. So he is also looking for magnetization as function of magnetic field, but he is doing it for antiferromagnetic spin. And he arranges the data going from higher temperature to lower one. So at higher temperature, it starts from zero magnetization, and then magnetization goes linear with magnetic field. If one lowers the temperature, the slope becomes sharper. If one lowers temperature further, then for some range of magnetic field, the system resists to being magnetized. So it wants to stay antiferromagnetic and resist to external magnetic field. So this high temperature is similar to paramagnetic, and it follows theory wise law where magnetization is proportional to magnetic field. This proportionality coefficient is inverse to temperature. And if we go to really low temperatures, then the dependencies become a little crazy. It is not as simple equation, and it is interesting to analyze. So it's something novel that may not be available to people. Okay. I just completed reviewing what you're doing so that you are aware of works with each other. Now, the research procedure, you already run the tool, make the figure, change parameter, report stuff. And for organizing the data, you already did it. Right? Now, how to write your report. We are not the first people in the world who are speaking in public or writing something for other people who are. So there are several ancient cultures along the world, and I'm just a little bit more acquainted with Western countries, but there are analogs in other cultures. So in Western culture, there were ancient Greeks who, it's like 3,000-4,000 years ago, who were making philosophical conclusions on what's the best way to present scientific results of the thermodynamics class, but generally how to share your thoughts with other people so that they listen to you and perceive it. And Greeks were looking more on the philosophical aspect and just making reflection of the first one, designs, collects results, thinks about style, arranges the results of logical thoughts in the most reasonable way, and then thinks how to present. But it was more philosophical rather than practical. In the ancient Rome, the direction of thought was more practical and oriented to achieving some visible results. And there was a public speaker and philosopher, Cicero, who gave some suggestions how to write reports in thermodynamics. How to speak in public. And according to his thoughts, each public presentation has 3 goals. I'm aware of them, but I'm not a good example. I'm failing all of them, but just bringing this information to you. Does anyone in class study Latin in some level? No one? Okay, then no one could check if John, you did?
Long time ago.
Hey, can you please try to read first 3 words? Because I will fail the pronunciation, maybe you do better.
It could be wrong. I think it's delectare, docare, movare.
Okay, yeah, thank you. So, which means to please, teach, and to move. Which means any public presentation has 3 goals: to make whoever listens to you to be pleased, like to tell jokes or sing or dance, to communicate some new information, because humans are curious by their nature, and then to move. If you are speaking to someone, it means you want a person to do something. Or maybe not to you, for someone else, but we do not speak just to radiate something. There are typically goals. And there are practical recommendations from this Cicero. We see this statue. So, according to Cicero, each writing or public speak does have 6 sections. So, and I'll probably ask John to help a few times more. So, can you read the full word?
The first one?
Huh?
Exordium.
Okay. So it means to catch attention of the audience from the first word, to tell something like, I will save the world from Star Wars, or we will design how to design a drug against cancer, or you'll get free electricity to everyone. Something that is, or like I don't have good examples, but tell something interesting before audience falls asleep. And ideally summarize what you're going to talk about. In scientific community, people call it like title and template. But sometimes titles and templates are not following CISOR because they're boring, but they shouldn't be. So, John, please help with the second full word.
I'm not sure if Latin has the noise or not, so it's either narratio or narratio.
Okay, yeah, thank you. So it's similar to English narrative, but here it means the summary of how the problem we are talking about was addressed by others. Like what is the state of the problem? And in scientific community, it's more review of literature or copy paste of some famous equations from the books. So we are standing on shoulders of giants, and we should give credit to these giants, right? So the next third word, John, please help.
Partidio.
Yeah, thank you. So it's like partition function in thermodynamics. So divide or split. If it is talk, public talk, it is maybe outline slide. If it is book, it is table of contents. If it is something in the middle, if it is a short report, you can give the names, summarize what you are going to get right away to help audience to follow things. So it's like in math classes, when theorems are proved, first one formulates theorem and then provides the proof. I was trying to practice it in the class, maybe not successfully, but give the main message of that you're going to deliver right away, and maybe give a little plan, outline how you're going to write. So the fourth one, John, please help.
Confirmatio.
Okay, yeah, thank you. So it sounds like English confirm. So you are providing proof. So in analogy to scientific activity, it is tables, figures, objective data. So you can just provide them, leaving the discussion for the later. Just objective data that probably will prove your main statement. Now, John, please help with statement number 5.
Confutatio.
And how will you translate it?
I don't know.
Me too. But when you are writing something for some audience, or if you speak publicly, you may anticipate even before you start speaking or writing that not everyone will agree with you, and so there will be like disputes and healthy discussion, or maybe even sometimes unhealthy discussion, so that someone in the audience will not believe you and will ask you to provide additional arguments, or will tell like, I see that everything is wrong. Explain me why. It's quite frequent situation, and you should be ready for it. So to prepare for it, you can try to be critical to yourself, design aggressive questions against yourself, and then design an answer. And if you think about it ahead, you'll be ready to address questions when they arrive. So it's really a simple thing, but it is psychologically difficult because just thinking of myself, I feel emotionally attached to anything I produce, and it's very hard to criticize yourself. But if you do it, you'll be unbeatable in public writing. John, please help with the last one.
Para-radio?
Okay, so it looks like medical prescription. Take a tablet, para-ratio, like by the mouth. But here it means conclusions, and I like this. It sounds funny, and I took it just from Wikipedia. So, in addition to summing up argument, you need to blame anyone who potentially disagree with you, and arouse positive feelings for the speaker, for the client, and for the case. So, summarize what you did in the favorable way. And this little funny things come from the reason that these ancient speakers primarily used those skills for lawsuits, to serve as attorneys or prosecutors, to convince the judge. And there, it was a blend of the logic plus emotional component. But for science, it's less emotion, more objective data. So now you have general idea what to write, and let me go in a few more things. So if in large, long, true world papers, it's like abstract introduction methods without discussion conclusions, right? If we are writing short reports, we do not have time for 6 sections. Probably we can arrange only 4. So in introduction, why the system is interesting. If you have some references you can cite them, do not worry, just 1, 2, 3 references will be fine. It's very clear that time is limited. Basically, I anticipate that this report will be reading like 2 hours. Maybe some of you need a little bit more, but do not waste much time. Just be brief and just think how others will read. So do not go over 4 pages unless you really got an inspiration to write that. Okay, so identify open problem of the system. Even if you haven't thought about it, it's quite healthy approach that will help humans to understand what you're doing. So it's like detective story. In the introduction, you can always present a challenge, present an open question. And even if you started this research before you saw any challenge or question, there is a little trick. You open your results, you look what is most exciting about them, and then you do reverse engineering. You design a question for which your results will be a good answer. No one knew whether the heat capacity will be sharp or shallow. It's so important for humankind. Maybe through this work we will answer. So it will intrigue the reader. And you cannot go over some waters because audience sometimes is literate and will understand if you make enough some argument. But just if you do fair game, just little change the accents, it really helps if you have the challenge. Then second thing, you can offer hypothetical answers. So you can tell if temperature is low, there is no thermal boiling, so any peaks are expected to be sharp, for example. And then you can declare that you hope and believe that this computational modeling can prove this hypothetical answer. But let's check yes or no. So next section is method. So with understanding that we are doing everything on a very quick and short mode, you cannot. It's not a dissertation. It's not a big paper, but the general attitude for the methods is to help reader to reproduce your result. Or if we speak cynically, to help reader to believe that he or she can reproduce your result. So give some general principles, mention some general principles that you use towards generating your result. If you have in mind some equation, either that you designed or you borrowed from the literature, in methods, it's really good. Please do not quote computer code. It's obsolete. People were doing it in the 70s, but now no one does. So if you want to mention some procedure, either do a figure in this flow chart or write an equation, which you're coding in Codon. So equations are very appropriate. The next section is results, where you show tables and figures. Figures are much appreciated if they have several lines and multi-panel. Also, there is a tradition to mention objective information that you generate 2 times. First time, briefly, each figure has a caption. Figure 1, schematic diagram. Figure 2, heat capacity as function of temperature at different magnetic field. And maybe mention brief trends that you observe. And then, and this is like a unit in your paper. And then second time, when you describe your results in the results section, you are writing freestyle text. As we see in figure 1, the heat capacity depends on temperature. There are interesting trends. So in some sense, there is a little redundancy. You are telling briefly in figure caption and more detailed in the results. And if you are in doubts, do not write more than 1 paragraph per figure. And because of our constraint, even if you are shorter and briefer, it's fine. So do not, I just know that from previous years, some class of NDs of similar classes were writing like 2 pages about each figure. No, do not do it. Just briefly what you observe. If you have an idea to explain why results move this way, it's really great place. And since we do not have discussion, you can blend a little bit of discussion into here. A little bit of explanation and connection with to others. Okay, and then we go to the last section, conclusions. When you are acting not more as a scientist, but more like an ancient speaker, when you try to induce positive feelings to your case, and you try to convince anyone who reads that your results support your hypothetical. Okay? If you created question and answer smartly, it will anyway. Right? But you need to convince. And also, you should provide some argument why your results are valuable and when they are trusted. For example, if you are studying paramagnet with J equals to equal to 0, and your results reproduce Curie-Weiss law, where the magnetization is linearly proportional to magnetism and inversely proportional to temperature, then you tell the results are coinciding with known experimental facts for any paramagnets, therefore they're available. And if you're doing something else, you can trustable either the reasons for results to be trustable, either coinciding with experiment or being logically perfectly connected. So if you mention it, and then a couple of references, which it could be scientific papers, it could be pages from Wikipedia, it could be textbooks, it could be works of your classmates. For example, the works by Sophie, John, and Crystal can be cited by others as a fundamental for the. Okay. Other questions about this suggestions? And how are we doing this time? Is it? Okay, and I'll briefly go over a few other things. So this is a little bit about motivation. About it's a little funny and exaggerated, but I was giving this material to undergrads who are not sure why research is needed, and it's a little funny and oversimplified. But generally, like, the research that you do through your discoveries and publications and patents to the industry, and provide energy, new technologies, and then regular citizens are benefiting it, pay taxes, and the government gets funded and repeat the cycle. Right? Or other way, if you are affecting the education, then you are helping to generate workforce, if you become future scientists, to the industry and help to propagate this new tools and things that help citizens just through funding return them. Or through education, you just provide general literacy to the public. So it is just a backup if you do not know how to explain motivation. But I think you can do much better than. So discussion is a natural part of scientific life. So do not be surprised if on the presentations there will be visitors who will try to argue with you. Just think about how to criticize yourself and what to prefer, and you'll be fine. And the same for the writing. So just maybe put a sentence. One can wonder why the line doesn't behave other way, but here is the answer. So just accept the possibility that someone disagrees with you, and you may have some idea of what to just prepare mentally and emotionally. Okay, basically I'm done, but I want to show the reviewing forms that you will be filling on the. So we are mimicking the deep web, where you submit to American Chemical Society or some other journals. Basically, there is an editor-in-chief who looks on your paper and sends it to reviewers. And editor requests reviewers to be critical to you and gives some criteria. The criteria here are basically borrowed from the real life, but they are a little bit exaggerated in more detail. So results are outcome of reviewers' report are like published as is or rejected, which is rare, and typically it's like major revision or minor revision. All reviewers are requested to summarize how did they first understood the paper. So maybe in 10 words, after you read works with other classmates, summarize how you understood what was done, what is managed. In the introduction, you tell either big picture, either motivation, other challenges. And you're like, oh, yeah, the author gives an interesting challenge and probably will answer. If there is an attempt to provide a hypothetical answer, reviewers are encouraged to mention it positively, because it really helps. Also, reviewer may mention who are potential readers of this book. Is it only graduate students in thermodynamics, or it is anyone who deals with magnetism, or any chemist, or any physical chemist, or it is broad public, including kindergarten children, is the best possible positive way to tell that the paper is good. So if it is useful for general public, it is good. Okay, quality of figures. Right now, we all are computerized, but not long ago, papers were published only, not in print, but only in printed version, and distributed to libraries often without color, in black and white, and sometimes scientists were cutting on Xerox and quality were reducing drastically. So if the lines are not thick, it will be not possible to see what it is. So try to analyze when you are reviewing someone, give a credit if it is a thick bold line. I can criticize if they are like if there are dots, dashes, symbols that help to follow it. And if there are no labels, there is no attempt to put units, there are no captions mentioned. If you do not know what are the units, just try AU, arbitrary units. It's better than nothing. Captions, like basically mentioning if the author whom you're reviewing made an effort to explain people in So logical organization. If the author is following some logical steps, it is immediately visible. It's just this question, it sets a barrier against those who are blindly throwing all data without any system into the report. So just check if results are followed from each other and the connection between figures is explained. So if you see it, you're ready to the list. Conclusions. If conclusions refer to challenging hypothesis from introduction, give a credit to the author. If it is supported by data, say yes, please do. And if you want to say a good word about paper, you can tell that I found new knowledge. The paper is transformative because as a reader, I learned something new that I never knew before. So if the reviewer tells this, worth it to after final decision by editor. And which statements in conclusions inspire you to do similar type of work? In some sense, it is not so much applicable because we are all doing the same style of work, but we can pretend be quiet. And the best possible emotions that reviewer can communicate to editor are good form of jealousy. Like, oh, why didn't I start this subject? It is so interesting. The results are so interesting. I probably start the same research as this author right away. So if you, as reviewer, sees something interesting in the work you are reading, do not hesitate to do it. It's always appreciated and it is promoted to the highest term. You can tell if you believe the general public will benefit from this work. Results clearly presented. If in the results and discussion, the elementary mechanisms are identified and presented. It is what we did by comparing the energy as function of temperature and the results from crystal about the width, right? When we tell that magnetic orders are populated, if magnetic field is big. So trying to not just report objectively the image, but provide some explanation. Another thing, number of figures and tables adequate. From what you sent to me, I saw that some of you are really energetic, inspired, and in this class, several attendees generated like 13 pages of figures. It's cool, but it is not a format of a group report. So combine and select only the best one. So if you see 30 figures, I hope not, but if you see as a reviewer with some, please reduce, make the number of figures smaller. If you see a report without figures or with only one figure, you also can suggest maybe amount of objective information is not sufficient. So just help to adjust to better stuff. And also, if some figures or tables are not referred, not mentioned in the freestyle text, you can complain about it. So basically, only those figures that are explained in freestyle logical description I need. If there are some figures just for decoration, recommend author to remove them. Which equations and numerically solved in this work? We discussed it and mentioned Monte Carlo. If there are equations but they are not explained, you can compare. Again, I anticipate that there will be reports with no equation or a couple of equations. But if there are, just help authors to be good. Okay. I would not ask this question because we all are in the same boat, and because you were already provided the info. But if the unbiased visitor will come and listen to you, it's quite a typical question. Like, if you decided to study anti-thermal, why did you elect to use Monte Carlo? Were there other methods available? Nothing else is available, but think about it. And it is standard question. Methods trustable. I want to say yes, but if you have doubts, express them. It's better if you criticize as authors yourself, or as reviewers, you may criticize the author. That author is not critical to himself or herself and doesn't check that. And any other comments? Okay.
Could you elaborate a little bit more on that last one for HBE and HSE 06?
No, neglect this red line. It is a heritage from computational chemistry course. Of course, I can answer it, but it is not related to what we do.
Okay.
If one computes electronic structure by density functional theory, there are several ways how to account for electron-electron interaction. There are several standard methods. The general gradient approximation by Ertenhoff is most standard, and the height-Kuzari Ertenhoff includes additional terms and helps formation of excitant, which is important for optical emitter. And comparison of these two methods is good if you have computational chemistry. Here we are doing physical chemistry, modern approach, so I just didn't have time to remove the slide. Okay, done. Everyone is welcome to disconnect. I'll stay here to answer questions if any, and please consider to either come to the class with 3 printed copies or submit. Maybe let's if you come in class, it will be easier, but maybe submit as soon as it is ready as an email. And if you are really short in time, you can do it. I'm not telling literally midnight of Tuesday, but maybe I'll check early morning before class and we'll prepare files to share with everyone. So like 7 a.m. on Wednesday probably is the deadline for electronic form. Make sense? No objections? Okay. Send me emails if any help is needed, and do not put more than like 4 hours maximum for this. It is expected to be a quick report. Meeting is done. I'm going to disconnect after counting to 3. Any questions 1? Any questions 2? Any questions 3? So adjourn is announced. Meeting is dismissed.
Thank you, Dr. Keelan.
Thank you, John.
Thank you.
Thank you. No, the whole report.
Yeah, but I mean before, like you showed some sort of simplified, like
Yes. It was not mandated.
okay.
Some classes in this were asking for feedback and suggestions and were sharing intermediate data.
Okay.
It was not mandated. There was no extra credit, no punishment for doing or not doing it.
That's nice. All right, thanks so much.
Well, what's the first?
So, you presented some figures from the right?